Okay, this is about sine and cosine rules, and also the area of a triangle as relates to non-right-angled triangles. Now, just a recap for right-angled triangles, which I assume you have covered. We've got three main rules that help us to do calculations in relation to these things. First of all, there's Pythagoras, which is the sum of the squares equals the square of the hypotenuse. Hope that rings a bell. We've got SOHCAHTOA, which is a little mnemonic for the trigonometrical ratios that we will use. So SOH gives us the sine of an angle is equal to the length opposite divided by the length of the hypotenuse, and then we've got the same cosine and tangent in there. And then we've got the area of the triangle's half base times height, which actually applies to other triangles anyway, but is particularly convenient when we talk about right angle triangles, because therefore the height or the base would be the length of one of the sides. Now, if the triangle we're dealing with is not right angled, or let's say we don't know that it's right angled, because we haven't been given that piece of information, then we would use these three rules, the cosine rule, the sine rule, and the area of the triangle. So if we just look at this triangle here, and I've annotated it as with the vertices as A, B, and C, and the sides as A, B, and C, the A being opposite the angle A, and so on. So the cosine rule, for instance, a squared equals b squared plus c squared minus 2bc cos a. So that's kind of quite a useful formula. Now, if our triangle in our particular problem does not have the same letters, then we may have to restate this. But as with all these formulas, basically what we need to do is we need to kind of line up the values of what we know and what we want to know, and all being well, there's four things here, aren't there? There are three sides of one angle, so if we know three of those, we can use it to calculate the other one. So if we've got all three lengths, we can use it to calculate the angle, and if we've got two lengths and an angle, we can use it to calculate the other length. And now we may need to not only kind of rewrite it with the letters that are given in the problem, but also we may need to rearrange the formula to make it explicit in the actual algebraic value for the quantity we want. So that's the cosine rule, and the sine rule is a over sine b equals b over sine b equals c over sine c. I mean, typically we kind of just use, this one equation here. Of course, seems almost too simple to be true, doesn't it, really? It also means sine a over a equals sine b over b as well, of course. So that's the sine rule, and then the area of the triangle, half AB sine C. So if we look at this example here, then the area of this triangle would be the product of these two sides, A and B, times the sine of this angle here, sine C. So so those are the three formulas we will tend to use. Now, you may well ask what happens if one of the angles is obtuse, this example, or acute. But if one is obtuse, then we may well find that well, in actual fact, the formula still work basically. The cosine of this angle is going to be negative. The sine of the obtuse angle is positive, but without going into too much detail, then essentially the formulas still work. And of course, if we have a right angle triangle here, then they still work as well. And interestingly, if, for instance, well, in this triangle here, I've denoted the right angle as C, but if we denoted it as A and compared it to this formula here, then the cosine of 90 degrees is 0. So in actual fact, this term here would disappear, and we'd be left with a squared equals b squared plus c squared, which of course is Pythagoras' formula. So that's a little bit of the background. Let's just have a look at one or two examples then. So calculate length df in this triangle here. Okay, we've got two sides, got the angle here. So I've that shows D, F, and G. So I've marked the lengths D, F, and G with small letters. Here is our formula: a squared equals b squared plus c squared minus 2bc cos a. Yeah, hopefully you'll be able to just kind of recall that, have instant recall for it, but chances are it's going to be on the sort of the front end of any examination paper you've got. So probably don't need to worry about it, but I think if you have a bit of practice with these questions, then you'll just recall it anyway. Right, so applying the letters that are specific to this example, we've got g squared equals d squared plus f squared minus 2df cos g, and we can just substitute in. I mean, it's already explicit in g, so we can just substitute in our d or our f, and of course our angle g here. And if we work that through, we can just plug those things into our calculator to give us g squared, and then from that g is going to be 6.01 centimeters to 2 decimal places. Okay, I didn't quite look at it there, but this is not to scale. We say not to scale, and the truth is that, of course, this 10 looks a bit short, and the arrow angle looks a bit big. All right, so so that's that example. Let's look at this one. So this now is an example with an obtuse angle. So we're just going through the same process again. We've got Q's and P's and R's, and instead of A's and B's and C's. So we adapt our formula here like this, substituting our values. The cosine of 120 is actually the same as the negative of cosine of angle 60. I mean, it won't matter if you just plug it into your calculator anyway. And we will find from that Q actually works out to be, all this lot is 171. That works out to be square root of 171, therefore, and that gives us 13.08 to 2 decimal places as that figure. Yeah, well, 13 is sort of in between the longest and the sum of the two sides is between 9 and 15, so kind of makes sense. Just a little thing here. If it had been an acute angle here, I might not actually kind of work too well. Probably should have drawn that at 60 degrees. Then we'd see actually, therefore, that PR, we would have got an answer for PR. It would have been much shorter. Of course, that just kind of helps to illustrate the fact that we can use obtuse angles in our with our formulas. ABC is a triangle. Work out the length, work out the area of triangle ABC. So here's our area formula. Well, here, this is fine. We've got the two sides and the angle in between, so this couldn't be more straightforward, really. Half AB, I mean, sine C. In fact, all the angles are labelled the same as the formula, aren't they? So that comes out to 18.2 if we take that to 3 significant figures. So just pop those straight into our calculator. And it gives us the answer. Another one here. Diagram shows a parallelogram EFGH with the measurements on, and work out the area of the parallelogram. Well, we can it's parallelogram. So if we draw this diagonal and think about this triangle here, EFG, then again we've got two sides and the angle in between. Yeah, so we can just plug sine 106 in there, which is actually the same as sine of 74 degrees. If you put sine 106 in your calculator, you will get the correct answer, and that comes out to this figure here, 6.57, etc. We double that, get the answer, this being the area of the whole parallelogram. Okay, so yeah, that's another application of that one. Try this one. A triangle has sides of length 8, 10, and 14. Work out the size of the largest angle. Your answer to one decimal place. Well, here I've drawn it. Now, the largest angle is going to be opposite the longest side, isn't it? So we've got three sides and we want an angle. Okay, so here's our formula. Now, if we rejig this, change the subject to the formula. So we've got cosine of A is the formula. We've got all these values on the right, and just substitute in our 8, our 10, and our 14 into there, and we get minus 1/5. Right, and the reason it's minus is because it is the cosine of a negative angle. So we need the inverse cosine of this ratio to give us the angle. So that's cos minus 1 on your calculator. And so if we put in cos minus 1 of minus 1/5, then it will give us this angle here, which is 101.521 decimal place. Okay, so and this example here, which I think was the last one. Right, here's a triangle. Find the value of x. So in this one, we've got two sides. So we're looking at what we know and what we want to know. Two sides, two angles. That would be the sine rule. And here is the sine rule. And here it is reorganized. We've changed the subject to the formula. Sine B as the subject to the formula. And so if we just plug B and the sine of A, which is 72, of course, divided by 54, well, so that's 31 times sine 72 divided by 54. It gives us this value. Now, this is the ratio. This is the sine of angle B. So we want the inverse sine of this ratio to give us an angle. So B therefore is sine minus 1 on our calculator of this value, and that's going to give us 33.09 degrees to 2 decimal places. Okay, so some examples there covering all three of those formulas, and also got obtuse angle example, a couple of them in there as well, just to give you the idea for that. So hopefully that's going to be of use to you, and thanks for watching.